What's up, guys? It's Mr. Brengle, and we are going to talk about part 2 of the energy math. Okay, in this case, this is the learning sheet 4 for energy. So we're now going to take the math that we just learned about, and we're going to combine it with the energy bar charts that we talked about previously. So, and then we're going to kind of make an energy conservation equation and show how the energy is transferred from one thing to another. Okay, so here it says a cart is moving at 5 meters per second, and it collides. Real quick, I'm going to go ahead and underline it's 5 meters per second. So that's this one right here, cart A, or position A rather. Okay, and then it collides with the spring. So that is position B here. Okay, now notice that the velocity is 0 meters per second. That's this part right here. It says, at the instant that the cart is motionless. So it's saying that the cart moves in here, and it compresses the spring, and at some point that spring's going to stop moving, right? And just for a brief second, the cart and the spring are motionless. It's very similar to when you throw an object up in the air, and at the peak of its trajectory, its vertical velocity is 0. It's temporarily motionless. Same idea here. Okay. It says, what is the largest amount that the spring could be compressed? Okay. So we're going to be solving for the compression of the spring here. And it says, assume no friction. Okay. So the first thing that we want to do here, this chart and everything, is it says define the system with the energy flow diagram, then complete the energy bar graphs qualitatively. So we're actually going to draw the bar graphs on here ourselves. And the system / flow, we're basically just going to list everything that's involved here. So when we talk about the system, you know, the system is similar to the zero reference level that we talked about with gravitational potential energy, in the sense that you get to set it, you know, as to whatever you want. The system is relative. Okay, so that means that, like, if we're talking about the system of energy that, let's talk about heat on the Earth. Well, we get heat from the sun. So if we define the system as the sun and the Earth, then that energy is within the system. Versus if we define the system as just the Earth, then that means that the energy that the Earth, quote unquote, gains due to heat is really coming from the outside of the system, right? The sun is inserting energy into the system. It's doing work to the system. So it's really just kind of changes how we word those things. Is the energy already in the system, or did it enter the system? Okay, so let's go ahead and list out everything here that we have, which would be like the cart, the track, the spring, and we're also going to put the Earth. Now, we put the Earth on there really just for like gravitational potential energy. There is no gravitational potential energy in this problem, so we won't really use that, but we will in the next one. So now, for position A, so we are only looking at this right here. What type of energy does the cart have at position A? Well, it's moving on the ground. It's moving 5 meters per second on the ground. So assuming that this level right here is 0 meters of height, then we would say, okay, well, this object clearly has no gravitational potential energy because it's on the ground. And then at the same time, it also has no elastic energy because it's not in contact with anything that can be stretched or compressed. So this object must have kinetic energy because, well, we know that because it's moving, but it must be all kinetic energy because it doesn't have the other two types. So we don't need to know exactly how much, but what we're going to do is we're going to mark on here how many bars of energy does this have. And you can just draw this on your chart, literally, or on your paper just like this. We call these LOL charts because when you draw them out, you would just draw your LOL. There's your first chart right here, your system, and then your second chart. Okay. So what we're going to do is we're going to go ahead and mark one. You know, this is 1, 2, 3, 4, and 5 levels, so to speak, and we're going to draw our bar chart all the way up to the 5th level. The only reason why that's important is that if we have 5 bars of energy on the left side, then we must have 5 bars of energy on the right side. Because remember, all energy is transferred from thing to thing. We can't create or destroy it. Now, if you wanted to start with 4 bars of kinetic energy, that's totally fine. Just make sure that for position B over here, that you only have 4 bars of energy, okay? So now let's look at the second situation. Let's determine what type of energy is involved with situation B. Here it shows that the cart has compressed the spring, right? So, and it's not moving. Since it's not moving, we know that we do not have kinetic energy. Since it's still on the ground and has no height, we know that we do not have gravitational potential energy. But because the cart is in contact with the spring and the spring has been compressed, we can now show that the cart has elastic energy, right? So all the kinetic energy that the cart initially had has been transferred into the elastic energy that's stored in the spring. And we can go ahead and talk about that with the car because the car is in contact with the spring. For all intents and purposes, it is an extension of the spring at this point. So I do want you to notice that we have 5 bars of kinetic energy on the left side. We also have 5 bars of elastic energy on the right side, position B. So this works out. This is just showing us that all the kinetic energy from the car was transferred into elastic. Okay. So for part B here, it says quantitative energy conservation equation. Well, what we're going to do is we're going to basically take this right here. We just said that the kinetic energy on the right side, okay, was then transferred into, so it must be equal to, all of the elastic energy on the right side. Okay, so what we can actually do is we can now write out these equations a little more full, right? Kinetic energy is 1/2 times the mass times velocity squared. And then we're going to set that equal to 1/2 times spring constant times stretch squared. So this right here would be your energy conservation equation. It's showing you that the kinetic energy that was initially in play is equal to or transferred into the elastic energy. Okay, and we can actually now calculate, if you remember, it asked us what is the largest amount that the spring could be compressed. So if the car moves in at this speed with this mass, how much can it compress this spring right here? Okay, so we are going to be solving for the stretch right there. Okay, so determine maximum compression of the spring. Now, since both sides of the equation have 1/2 in them, we can actually just get rid of that. So there's 1/2 right here, and there's 1/2 right here. Since it's on both sides, let's just get rid of it. Let's rewrite it as mass times velocity squared is equal to spring constant times position squared. Okay, and then we can go ahead and plug these things in. So it's going to be 8 kilograms times the velocity squared, which is 5 meters per second squared. That's equal to the spring constant, which it tells us up here is 50 newtons per meter. 50 newtons per meter times the stretch squared. Okay? So when you do 8 times 5 squared, which, 5 squared is 25, and then times 8, you're going to get 200. So I'm going to kind of, let's scoot down just a little bit here. So we'll rewrite this here. So this is going to be 200 is equal to 50x squared. So we now need to divide by 50 on each side. Okay. And that is going to give us 4 is equal to x squared. We then, of course, need to get rid of the squared, so we will square root both sides. That will cancel there. And then we find out that the maximum stretch, the change in position of the spring, is going to be equal to 2 meters at its maximum. So when that cart comes in and hits that spring, it can compress at 2 meters. If you think about that, that is a large spring. 2 meters of compression there. So that'd be 2 meter sticks that could compress. Okay, so this is a more, I think, practical use of like combining the things that we've learned so far. So you learned about the bar charts, kind of basics. Now let's make our own bar charts and let's add in the math that we just learned about. Okay, so there's number 6. I would love it if you guys would give number 7 a try on your own, and then check the video to see how you've done. Okay, so you can pause this if you need to or whatever. But I'm going to go ahead and move on here to number 7. Similar situation here. So this time we've got, so there's, just actually to keep things consistent, we'll just keep it as red and blue for our situations here. Okay, so it says a rock is shot straight up in the air with a slingshot that has been stretched 0.3 meters. Assume no air resistance, and then tells us to do the same things. And eventually, at part C, it does tell us to solve for the height that the rock can reach. So basically, what we've got here is we've got the slingshot. Got the slingshot right here, and it's being pulled back, and you can see that the stretch of the slingshot is 0.3 meters. Okay, so then the spring constant here is 100 newtons per meter. Okay, so in the first situation, what type of energy do we have? Well, let's look at kinetic energy. Is the object moving? No, the object is not moving, so it can't have kinetic energy. Is the object above the zero reference level? Answer to that, no, because the zero reference level is defined right here as the location that it's pulled back to. Okay, so that means it has no height and therefore no gravitational potential energy. The only type that we're really left with here is elastic energy, and that makes sense because the object is being stretched back in the slingshot. So let's go ahead and put in 5 bars of elastic energy. Remember, it does not matter how many bars you put there, as long as it matches the final side. Okay, that's the key. So if you started with 4 bars instead of 5, that's totally fine. Just make sure that there's 4 on the right side. Okay, and real quick, I did forget to define the system here, so let's do that. That would be the things that are involved: the rock, the slingshot, the earth. Okay. Now don't get earth and ground mixed up. Okay, so look, if I said that the ground was part of the system, that would be talking about the surface that the object is on. When I say the earth, I'm talking about like the earth, the whole thing. That's why we put that in for gravitational potential energy, because we're in reference to that when we're talking about how much gravitational potential energy something has. Okay, so now let's look at side B here. So in situation B, it shows that the rock is now up here. It has gone up in the air after it was shot. It does give us the mass, and it tells us that the velocity is 0. So it is implying that the rock has reached its peak. Okay, so since the velocity is 0, we know that there's no kinetic energy involved here. Okay, the object does have a height now. We don't know what it is, but we know that it has gravitational potential energy, so let's come back to that. And then the rock is no longer in contact with the slingshot. It is not stretching the slingshot anymore, so there is no elastic energy. And then it tells us not to, it says assume no air resistance, so that would be your thermal energy over here, your friction. That would not be involved either. Okay. Now, if it was including air resistance, or in the previous problem, if we included friction, then we would need to talk about this thermal energy. So that's something that we can kind of discuss later. But so the point here is that all of that elastic energy initially from the slingshot was transferred into gravitational potential energy for the rock when it got to its peak. Okay. So we can go ahead and do the same thing that we did before and make our equation here. We started with elastic energy, and we showed that that was converted into gravitational potential energy. So let's go ahead and write out those equations like we did before. 1/2 kx squared is equal to m mass times acceleration due to gravity times the height. Okay, so once again, we can go ahead and sub in all of the values that we've been given here, which would be like this. This time we do have to leave this 1/2 in because it's not on the right side. So we're going to go ahead and write 1/2 times the spring constant, which it gives us right here at 100 newtons per meter. Then we need to multiply that by the stretch squared, so 0.3 meters squared. And then that is set equal to the mass of the object, which is 500 grams, which would be 0.5 kilograms. Okay, so 500 grams divided by 1,000 will move this decimal place 3 to the right. That's how many kilograms there are. Okay, so 0.5 kilograms times 10 meters per second squared. Remember that g is a constant, 10 meters per second squared. And then we are solving for the height of the object. Okay, height of the object. Okay, so if we go ahead and let's do the left side of the equation here. So 0.3 squared, that's what I would do first. And then multiply that by 100 and cut it in half. That is going to give you 4.5 is it equal to. And then on this side, you're going to end up with 10 times 0.5, which is just cutting it in half. So 5 times the height. So we just need to divide by 5 on each side there. And that is going to give us a final answer. A height is equal to 0.9 meters. Okay, so basically what this is saying is that if you take that rock at that mass of 0.5 kilograms or 500 grams, and you put it in a slingshot and stretch it back 0.3 meters, so 30 centimeters stretch, and that it has a spring constant of 100 newtons per meter, you let that thing go, it's telling us that its maximum height that it can reach is 0.9 meters or 90 centimeters. Okay, so that's kind of the idea there. All the elastic energy is transferred into gravitational potential energy. Okay, so I hope that this helps to kind of tie everything together, and we can certainly go into a lot more detail with this, but for the time being, this will be good and give us a good base understanding of this, and then we'll be able to do some more complicated work later. That concludes part 2 of your energy math on Learning Sheet 4.